All right, building off of what we learned in Chemical Bonding 1, which was Lewis theory and formal charges. We did a little bit of bond energy and bond length as well. We are going to be learning valence shell electron pair repulsion theory. If you've taken Chem 20, you've probably covered valence shell electron pair repulsion theory, at least in a little bit of detail. We are going to be adding on a couple of shapes. So in Chem 20, you would have learned 3 shapes. You would have learned 3 basic shapes and then some with lone pairs. We are going to learn 5 basic shapes. We're adding 2 more shapes on top of the 3 basic ones that you would have learned in Chem 20. We'll also add some other fun ones with electron groups or electron pairs, lone pairs. So valence shell electron pair repulsion theory. Valence shell is just the outside electrons, the ones that are on the periphery of our atom. The electron pairs in bonds and in lone pairs repel each other. That's all that valence shell electron pair repulsion theory is. Under valence shell electron pair repulsion theory, electron groups can be any of a lone pair, a single bond, a double bond, a triple bond, and a single electron like in radicals. Each of these is one group. So a double bond is one group, a triple bond is one group. They're not more groups because there's more bonds or more electrons there. They all count as one group. The repulsions between these electron groups on our interior atoms, oftentimes our central atom, determines the geometry. And by geometry, we mean the shape. The preferred geometry is going to have the maximum separation of our electron groups. So our electron groups, because they're repelling each other, they're going to try to get as far away from each other as they can. And typically we're going to start by thinking about what's the basic shape, and then if there's lone pairs in there or if there's single electrons in there, then we'll think about, okay, how does that change from our basic shape to one of our lone pair shapes? If you have 2 electron groups, you have linear geometry. In linear geometry, your groups are on opposite sides. The furthest that 2 things can get away from each other is complete opposites. So if you've got 2 groups, they're going to be completely at opposite sides from each other with 180 degrees, half of a circle, 360 degrees, 180 degrees between them. So this is our linear geometry. If you've got 2 groups, that's linear. What if we have 3 groups? If we have, oh, never mind, we're not getting to the 3 groups yet. CO2 also has 2 electron groups. They're just double bonds instead of single bonds. That's also going to be linear geometry. If you have 3 groups, like in boron trifluoride, those 3 groups can be separated by 1/3 of a circle, which is 120 degrees. So 3 groups is trigonal. Tri meaning 3. If I remember correctly, the gonal part means points. And it's also planar. Planar here meaning that it's flat, it's in a 2-dimensional plane. So this would be sitting on the board And this is like if you're doing the YMCA dance, if you got your feet together, you've got your hands out in the Y shape, this is the trigonal-planar geometry. Formaldehyde also has 3 groups. So BF3 had only single bonds. Formaldehyde also has 3 groups. It's got 2 single bonds and a double bond. It's still trigonal planar geometry, but the bond angles are slightly different. Different types of electron groups exert slightly different repulsions. So a double bond exerts more push than a single bond, for example. Which I think makes sense. If we've got 4 electrons, we would expect that to be stronger than 2 electrons. So the 4 electrons that are in the double bond push on these bonds between the carbon and the hydrogen, these single bonds, and that causes them to deflect a little bit. So rather than having a true 120 degrees, it's a little bit wider between the double bond and the single bond to make a little bit more space because of the extra electron pairs or electron pair that we have in our double bond. And so the single bond angle compresses a little bit. You would not have to know the actual degrees, but you should be able to make predictions about, is it going to be exactly 120 degrees? Is it going to be less than? Is it going to be greater than 120 degrees in a circumstance like this, in a situation like this? So this 121.9 degrees is bigger because the double bond pushes the single bonds away. And the single bonds pushing on each other isn't as strong as the double bond pushing on the single bond. So the single bonds get sort of forced to be closer to each other. Let's say that we've got a central atom in a 3-atom molecule. It forms 2 double bonds and has no lone pairs. What is the geometry of the molecule? So we've got 3 atoms. We have a central atom, and there's 2 double bonds. So we've got an atom in the middle. We've got atoms on the sides. Those would be our 3 groups. We've got 2 double bonds on the central atom. What's the geometry of this molecule going to be? Linear. The furthest that these side A groups can get away from each other is 180 degrees, so it would be linear. Linear is always going to be 180 degrees because it's just 2 things pushing on each other. The furthest they can get away is 180 degrees. So even if we had like a single bond and a triple bond, 180 is as far as they can get away from each other. It's not going to like deflect in some weird way. So that's 3 groups. With 4 groups, we have tetrahedral geometry. Our prefix tetra, we write 4 groups, tetrahedral. The tetra part here meaning 4, and the hedral part meaning sides. So this is the shape of a 4-sided die, which would often be shortened to a D4. one of the issues that starts to pop up once we are getting into 4 and more groups is that they venture into 3 dimensions of space. And so it can be a little bit harder to visualize. So if we were looking at something that has linear geometry, if our central atom is here in the middle where these balloons are tied together, the balloons are going to stick out opposite from each other. If we've got 3 balloons all tied together, they're going to stick out 3 dimensions in the plane. That's our YMCA pose. When we add in a 4th group, it's normal for us to think, oh, it's just going to be an X shape, but this is ignoring the fact that there's 3 dimensions of space. They're in an X shape, there's 90 degrees between them. But if we take advantage of the fact that there's 3 dimensions, if we rotate the top 2, so if you make an X with your body and you rotate, twist at the waist 90 degrees, now our hands and feet can stretch out a little bit more because we've got a little bit of rotation, and so they can actually get further away from each other in that way. So this is our tetrahedral geometry. This is what a tetrahedron looks like. Notice that there's 4 faces. The bottom one you can sort of imagine. We can sort of see it through the triangle or through the pyramid. And then we've got triangular faces, and there's the back face that we wouldn't be able to see. So that's a D4. And our bond angle for a tetrahedron, for a tetrahedral geometry, is 109.5 degrees. Again, that's a little bit more spread out. Than if it was in 2 dimensions. Because it looks, if we write it in 2 dimensions, it looks like 90-degree angles on paper. But again, that's ignoring if we have a 3rd dimension, which we do. And so it's actually is 109.5. That's, I think, the only really weird angle that we have. The rest of the angles make more sense. Like 180 is a nice round number, 120 is a nice round number, 109.5 is a little bit of a weird one. We'll also see some 90-degree angles. And then here's what I was saying on the previous slide, just written out. So again, it looks like it should be square planar, but if you rotate the 90 degrees, you get a little bit more separation, and that's tetrahedral geometry. What is the geometry of this HCN molecule, given that the Lewis structure is this? This one's also linear. 2 groups is linear. Identifying the shapes by itself, I think, is not so difficult. When we add on coming up with the Lewis structure before that, that makes it a significantly harder problem because we have to come up with the correct Lewis structure to be able to predict what the geometry is going to be. We're also going to add in more shapes, and that makes it a little bit more complicated as well. If you had taken Chem 20, this is probably where you stop, but we're going to add on a couple more shapes. If we have 5 electron groups, this is trigonal bipyramidal geometry. So we're seeing trigonal show up again. Again, I'm pretty sure that this is 3 points. So it's a pyramid with a base with 3 points on it. And then instead of being pyramidal, it's bipyramidal. So 2 pyramids. Pyramidal just meaning it's a pyramid. The pyramids that we're probably used to seeing have 4 corners at their base. the bipyramidal geometry, the trigonobipyramidal geometry has a three-pointed triangle. This would be the same shape as a D6, a six-sided die. So in this bipyramidal geometry, three of our groups are going to lie in the plane. They're going to be flat in our XY plane. We call those equatorial positions. On planet Earth, the equator is the waist, like the middle band of the Earth. So these are the ones that are flat, just going out in all directions. And then we also have groups that are going up and down, that are axial positions. So these are ones going up or down along what would be the z-axis, typically. And our angles are not all the same in trigonobipyramidal, so that can also add a layer of complexity. So our equatorial positions are spaced out 180 degrees from each other. So our top-down view is going to look like this. Where in this middle section, this middle dot, we're looking down along this chlorine, phosphorus, chlorine line. And so we would see spread out around it that YMCA shape again. So we've got 120 degrees of separation. If we look at it sideways, which we sort of have here, we can see that between our axial and equatorial positions, we've got 90 degrees of separation. So 90 degrees between equatorial and axial. 120 degrees between an equatorial and another equatorial. So the ones that are flat around the sides. And that's our 5 electron groups. We can also have 6 electron groups. And 6 electron groups, this is actually not a D6, never mind, because we do cubes for D6. For 6 electron groups, we also have octahedral geometry. The octa here meaning 8, and hedral here, like we saw in tetrahedral, meaning sides. And this one is a D8, an 8-sided die. In our octahedral geometry, we've got 4 equatorial groups and 2 axial groups, but the bond angles are all 90 degrees. So if we were to look at it from the top down, or honestly along any of our axes, we would see these 90-degree angles between all of our groups. Looking down along any fluorine-sulfur-fluorine line, you'll see this same perspective for SF6. That's the most spaced out that we can get them. Any questions about our basic shapes? All right, let's determine the molecular geometry of CCl4. if we're doing the molecular geometry of CCl4, we need to know how many groups are on our central atom. Carbon is going to be our central atom because that gives us the most symmetry. So we're going to end up with carbon in the middle, 4 Cl's on the periphery. To do the Lewis structure, we count up how many of each group we have and how many valence electrons they have. Carbon's going to have 4. Each of our chlorines will have 7, and we've got 4 of them, so that's 28. 28 plus 4 gives us 32 valence electrons. In order to connect everything, we need bonds. So we're going to put bonds between our carbon and our chlorine. We've placed 4 bonds, 2 electrons each. 2 times 4 gives us 8 bonding electrons. That's going to leave us with 24 remaining electrons. We can distribute those remaining electrons to our chlorines because they're on the outside. So we give 1, 2, 3, 4, 5, 6 to that chlorine. That's minus 6. 1, 2, 3, 4, 5, 6 electrons to that chlorine. 1, 2, 3, 4, 5, 6 electrons to that chlorine. And another 6 to our final chlorine. That fills up their octets. That also conveniently uses up all of our electrons. Now when we go and check our octets, carbon in the middle has 4 bonds. 4 bonds with 2 electrons each, that's an octet. Each of our chlorines has the same configuration, 1 bond and 3 lone pairs, that's 4 groups of 2 electrons each. So our chlorines are all satisfied with their octets as well. If we did formal charges checks, those would also pass with flying colors. We get zeros for all of them. Now we can figure out what's the molecular geometry, what's the shape of CCl4 because we've got a good Lewis structure for it. How many groups do we have on our central atom carbon? We have 4 groups. What is our shape for 4 groups? 4 groups is tetrahedral. It looks like square planar. It's not square planar. It's not actually what it looks like here. It's not this flat 2-dimensional shape. It is instead a 3-dimensional shape. And we can see that we hit our little X pose. Twist 90 degrees, that's our tetrahedral shape. Okay, so in review for our basic shapes, two groups is linear. 3 groups is trigonal, planar, it's flat. 4 groups is tetrahedral. 5 groups is also trigonal, but it's 2 pyramids, it's bipyramidal. Sometimes shortened to BIPY, B-I-P-Y. 6 groups is octahedral. So these are all of our basic shapes, and we can always start with our basic shapes. If we don't have any lone pairs, then that is our molecular geometry. If we have lone pairs, then our shape changes, or it can change a little bit. So how do lone pairs affect things? Lone pairs make things more complicated. So if we have lone pairs, anytime we've got groups, we can figure out the electron geometry. The electron geometry is the arrangement of the electron groups. Our electron groups are any number of bonds, single bonds, double bonds, triple bonds, as well as lone pairs and radicals, lone electrons. That gets us our electron geometry, and that's always going to be one of our basic shapes. So it's going to be our linear, trigonoplanar, tetrahedral, trigonal bipyramidal, or octahedral. Our molecular geometry is the arrangement of the atoms. So since it's just of the atoms, we want to ignore lone pairs and radicals. So we're only counting bonds for our molecular geometry. If we don't have any lone pairs, then our electron geometry and our molecular geometry will be the same. If the central atom has lone pairs, one or more, then the electron geometry and the molecular geometry will be different. So we'll have to start with figuring out what's our electron geometry. We'll make that shape, either with our body, with a model, or thinking about it. And then to get the molecular geometry, we need to pluck off, remove some of those groups without moving the other groups around. So the electron geometry, the electron groups essentially that are lone pairs and radicals, we just make them invisible. We like erase them from our mental drawing. Starting off with 4 electron groups with lone pairs. We've got things like ammonia. Ammonia has the chemical formula NH3. It also has a lone pair on the nitrogen. Since it has 4 groups, 4 electron groups, 3 bonds, 1 lone pair, 4 groups gives us the tetrahedral electron geometry. So we've got tetrahedral electron geometry. And we can do some but not all of these shapes with our bodies because we only have 4 limbs. Unless you count your head. Sometimes you can count your head. That gets you 5 groups. So we have our little X pose. We do our turn 90 degrees. And then if one of those groups is a lone pair, get rid of one of those groups and keep everything else the same place that it is. Now how many groups do we have? How many can we see? 3. We can see 3 groups. 3 means trigonal. But it's not flat. It's not the YMCA pose. Right? It's one of our hands is sticking out in front. It's not flat. We're not being a diva. One's sticking out. So it's not flat, and so it's trigonal pyramidal. So it's a pyramid now. It's not flat like the planar geometry. So it's trigonal pyramidal, molecular geometry, which we can also think of. That'll sometimes just be called shape. So it's one of our fun, more complicated shapes. The way that lone pairs work with our bonding angles is that lone pairs exert more repulsion than bonding pairs. Lone pairs are more repulsive typically than bonds. if we look at a bonding electron pair between two nuclei, sort of this like oblong shape, long skinny shape. And if we look at a lone pair, it's a little bit more spread out. And because it's more spread out, it takes up more space, so it forces everything around it to get pushed away a little bit more. Lone pairs are the man-spreaders of electron groups. So if we look at the molecular geometry of our ammonia, we would expect it to have 109.5 degrees between all of the groups, because that's the ideal shape. But because we've got this lone pair, we're going to end up with larger than 109.5 between our lone pair, where our lone pair's center would be, and the hydrogens. And then between our other groups would be less than 109.5. The lone pair is taking up extra space. It's pushing those groups to be closer to each other, compressing that bond angle. If we look at water, you can draw the Lewis structure for water. We've got a visualization of it down here. I'll write it out for us. One way that we could come up with this would look like this. We've got bonds with our hydrogens, and we've got two lone pairs on oxygen. We've got 4 electron groups. 4 electron groups, 4 groups is tetrahedral. Again, that's make the X shape twist 90 degrees. Then if you get rid of 2 of those groups, like since I'm sitting on a chair, I can get rid of my legs. And now this shape, it's not flat, it's not linear. It's pushed up. The arms are pushed up. That's what we would call bent shape. So the molecular geometry is bent. And for the bent molecular geometry, our bond angle is even smaller, because now we've got 2 lone pairs, and 2 lone pairs are going to take up more space than 1 lone pair. And that's going to force these hydrogens to be even closer together. So 4 electron groups, 2 lone pairs is bent. If we had one lone pair, that was our trigonal pyramidal. And these are shapes that you would have also covered, should have also covered in Chem 20. So it's not our first time seeing them, maybe our first time thinking about the bond angles, but it shouldn't be our first time seeing them. In these structures, we've got different repulsion between our electron groups, and this is important for coming up with some of our more complicated shapes. So our relative repulsion of electron groups, lone pairs, because they're more spread out, they're not nice and neat between 2 atoms, because they're more spread out, those exert more repulsion. So when these form, when they're figuring out what their shape is, they're going to pick the lowest stress, the lowest strain form that they can. So they're going to try to minimize the number of lone pair interactions. Ideally, we don't have any lone pairs right next to each other, because those are going to have strong interactions. And lone pair bonding pairs, so lone pair with a bond, is going to be less repulsion, less bad than that. Bonding pairs interacting with each other is our least stressful interaction. So we want to minimize lone pair interactions. This would be like if we were planning a party and we know that there's two people that are there, maybe they're exes, they really just don't get along because they had a terrible breakup. And so we might, if we're thinking about, okay, how can we lay out the party, we might think, okay, let's try to make sure that one of the friend groups is in this one room and the other friend group is in this other room, so that those two people, if they both show up, are not interacting with each other. Oh, this person really likes playing board games. Let's put the board games in this room. This person really likes talking about this other stuff. Like they like figures or action figure, like movies, whatever. We're going to make sure that the movies and the board games are in separate areas so that they don't interact with each other. That's what we're trying to do when we're coming up with shapes. But lone pair interactions, that's what we're trying to minimize. What would our molecular geometry be, our shape be, for a molecule whose central atom has 3 bonding groups and 1 lone pair? How many total groups do we have? 4 groups. So we've got a total of 4 electron groups. 1 is a lone pair. What's our shape for 4 electron groups? Our shape for 4 groups is tetrahedral, but then we get rid of one of those groups. Imagine, poof, get rid of one of those groups. You don't have to imagine because you've got me. So we hit our tetrahedral shape. We get rid of one of those groups. Now what's our shape? We've got 3 groups now, so it's trigonal. Flat? Not flat. Not flat, right? Because flat would be up here. Not flat, because it's back there. So this would be trigonal, pyramid, or pyramidal. We can also have lone pairs with 5 electron groups. If we have 5 electron groups with lone pairs, this is where we have to start thinking about interactions. Now, you don't necessarily have to be thinking about how do I make my groups maximally spread out so that I get the right shape. But if you don't want to think about it, then you have to memorize the shapes. Like you have to truly memorize them, put them on flashcards, practice them, be able to recognize them. Because you might come up with something that looks like this, which would be trigonal pyramidal, with 5 electron groups and 1 lone pair. This is not going to work, though, because we've got 3 90-degree lone pair bonding pair interactions. And 90 degrees is relatively close to each other. If we put the lone pair on an equatorial position instead of the axial position, we've only got 2 90-degree repulsions. So 90-degree interactions are higher energy than larger number of degree interactions. These are more stressful than these 120-degree interactions. So if we put the lone pair at the axial position, we'll have 3 of these lone pair bonding pair repulsions at 90 degrees. If we put it in an equatorial position, it's only got 2 90-degree lone pair bonding pair interactions, and so this is better. Two is better because it's less interactions, less of those 90-degree interactions. And so the shape that we actually get is this seesaw shape. And doesn't really look like a seesaw the way that it's up on the board, but if you turn your head to the right 90 degrees, and you imagine that this fluorine, sulfur, fluorine, this line is sitting on the ground, these fluorines now look a little bit more like a seesaw. Or if you set these two fluorines on the ground, now it sort of looks more like a seesaw, like you'd see at a playground at a park. Let's see if we can draw that. The kid on the left sat down a little too fast, so the kid on the right is flying into the air. So that's our seesaw. That's with one lone pair. If you have two lone pairs, those lone pairs also want to go in the equatorial position to minimize repulsions. Because if we put one on the equator and one on the axis, then we'll have a 90-degree interaction between a lone pair and a lone pair. That's really bad. We want to avoid those at all costs. And so instead they go on equatorial positions. Lone pairs just generally go in equatorial positions. This is not always true. We'll see examples of when this is not true. But for our 5 groups, they do go in equatorial positions because 120-degree interactions are less stressful. It's better separation than 90 degrees. So we've got 2 of these groups, and they're going in the equatorial positions. Again, this is to minimize their repulsions, and so the molecular geometry is T-shaped. T-shaped. So that's our T-shaped. What if we added one more lone pair? Where would we expect that lone pair to go? Would it go in position A, B, or C? It would go in B, because that puts it in an equatorial position, so then it's 120 degrees from the other lone pairs. And that indeed is what we see. So XeF2 has 5 electron groups. There's 3 lone pairs on the xenon. And again, the lone pairs go in these equatorial positions to minimize their interactions with each other. And so we get, this is another weird way that we can come up with linear molecular geometry. So we've gotten rid of the 3 positions around the outside. We poofed them away. They're no longer there. There's no atoms there. So it's just the top axial group, the bottom axial group, and then our center atom. So that's another linear pair. Moving on to changes that we can make to our 6 electron groups, our octahedral. So if we've got octahedral electron geometry, but we have lone pairs, we have one lone pair. Because we have octahedral geometry, all 6 positions are equivalent. We've got all 90-degree bond angles because of the way that they're spaced out. And so if we put in one group, you can put it literally anywhere. It's easiest to see this shape if we put it in the bottom axial position. This is square pyramidal geometry. So we've now got the 4-cornered base that we expect to see probably in a pyramid. If we connect to those corners, we can maybe see that it's a square pyramid shape. So we can get square pyramidal. If we get another lone pair, where can we put our lone pair in this shape that's going to get the furthest away from this other lone pair? It would be in the top axial position, the way that we've got it drawn out. So in XeF4, we've got 2 lone pairs, 4 bonds. Again, our electron geometry is octahedral. The molecular geometry is square planar. These lone pairs are going to be across from each other because this avoids lone pair interactions. All the positions are equal, so we should put them across from each other. And now we've got square planar. We've got 4 groups. They're flat because the lone pair on top and the lone pair on the bottom are pushing equally, so they're not getting pushed up or pushed down. So it's sitting flat. That is our square planar geometry. All of this and maybe a little bit more is summarized in table 11.1 from our book, Electron and Molecular Geometries. The way that we would read this table, zoom in a little bit so we can read the headings. We've got the number of electron groups that we have on the far left, and then a breakdown into bonding groups versus lone pairs. So the number of electron groups determines the electron geometry. So if we've got 2 groups, it's linear. If we've got 3 groups, it's trigonal planar. If we've got 4, it's tetrahedral. 5 is trigonal bipyramidal. 6 is octahedral. So those are all of our basic shapes. Our electron geometry will always be one of those 5 basic shapes. And then depending on the number of lone pairs that we have, that can change our molecular geometry. If we've got no lone pairs, then our electron and molecular geometries are the same. If we have lone pairs, then it'll change to something like bent or trigonal pyramidal or seesaw or T-shape or linear. And we looked at several of these. We didn't look at all of these, but we looked at most of these specific occurrences. So this can be a good reference if you're trying to make flashcards to memorize all of the different molecular geometries, or when you're working on the molecular models worksheet that we'll be doing, I think, next week. Let's imagine that we have a molecule with 6 electron groups. It's confined to 2 dimensions, and so it has hexagonal planar electron geometry. So this is actually flat. If 2 of those groups are lone pairs, where would we put those lone pairs? One of them is going to go at the 1 position, and the other one can go at either of the 2 positions, either of the 3 positions, or at the 4 position. Where would be the best place to put those? Would probably be 1 and 4, so that they're as far away from each other as possible. If we put them at 1 and 3, there would be an atom in the middle that would get pushed on both sides, and so they would still sort of be pushing on each other, and this poor atom would just be stuck in the middle. If we've got them on opposite sides, then we can compress these bonds between the 2s and 3s, and that'll alleviate some of the strain of having those lone pairs in there. Okay, to summarize, the geometry of a molecule is determined by the number of electron groups at the central atom. The number of electron groups is determined from the Lewis structure. So we need a Lewis structure. You have to have the Lewis structure to come up with the electron and molecular geometries. Each of these groups counts as 1 electron groups, lone pairs, single bonds, double bonds, triple bonds, and single electrons like free radicals. Any cluster of electrons is 1 group. So if they're all in one area, that's 1 group. The geometry is determined by the repulsions. Our electron geometry is a simple shape. One of those 5 shapes we covered at the top of the lecture. Bond angles can vary. Lone pairs are stronger than bonds. We'll just say bonds generally. Double bonds are stronger than single bonds. Which of these statements is always true according to valence shell electron pair repulsion theory? The shape of the molecule is determined only by repulsions among bonding electron groups. The shape of a molecule is determined only by repulsions among non-bonding electron groups. The shape of a molecule is determined by the polarity of its bonds. Or the shape of a molecule is determined by repulsions among all electron groups on the central atom. Is it determined by just bonding groups, just non-bonding groups? Is it polarity, or is it all electron groups? It's all the electron groups. They all contribute. Lone pairs and bonding pairs both count. So if we want to predict molecular geometries, we need to first draw the Lewis structure for the molecule. This is multiple steps, or it can be multiple steps. So we need to make sure that we know how to do Lewis structures, stuff that we learned how to do in Chapter 10. We need to be able to do Lewis structures to be able to do the Chapter 11 material. If you can't do the Lewis structures, unless you're given the Lewis structure, you won't be able to come up with the shape. Then we want to count up the total number of electron groups. Lone pairs, bonds of any multiplicity, single, double, triple bonds. Single electrons will also count. I don't think that we see those in any of our examples. And then determine the number of bonds and lone pairs, or single electrons would also count in there if we have them. And then we can either imagine them in our head, pose them out, refer to table 11.1 to figure out our electron geometry and our molecular geometry. I don't remember if I gave table 11.1 on exams last semester. I don't think that I did, but it's something I could have done. I could see myself doing that. All right, we want to predict the molecular geometry and bond angle of ClNO. And it is arranged that way. So it is Cl, N in the middle, and then O on the side. In order for us to figure that out, we would have to do formal charges, because oxygen could also be in the middle. We count up our number of electrons. Chlorine has 7, nitrogen has 5, oxygen has 6. We get 18 electrons. We're going to bond some stuff up, 2 bonds to get everything connected. Then we've got 14 remaining electrons. We can distribute those starting from the outside and working our way in. So our chlorine and our oxygen can each hold 6 more to get them up to their full octets. And then we've got 2 left, and those can go on the nitrogen. That gets all of our electrons on the board. Is this a good Lewis structure? Is this a complete Lewis structure? We're guessing no. Why not? Nitrogen doesn't have an octet. So we need to get nitrogen an octet. How many more electrons does it need? It needs 2 more. It currently has 6. It needs 2 more. So we need to bring in a double bond. Are we going to bring it in from chlorine or from oxygen? There's a correct answer. Why would it be oxygen? Let's look at both possibilities. It's not going to be both, but let's look at both. Consider both. So let's consider double bond with chlorine versus double bond with oxygen. Do we have a tool that can let us make a distinction between these two shapes? Starts with an F. Formal charges. So we need to think about our formal charges. Formal charges is also how we would figure out that the nitrogen is in the middle instead of the oxygen or the chlorine. So thinking about our formal charges, we want to chop our bonds in half. Or alternatively, you can just draw the ends of the bonds in, which is the way that I do it in my brain. And then we want to count how many dots are right next to each of these atoms. So in our left one, chlorine's got 2, 4 from lone pairs, and it's got another 2 from the double bond. So chlorine has 6. It likes to have 7. So it's got a 1 plus formal charge. Nitrogen in the middle has the same amount that it normally likes to have, which is 5. And then oxygen on the right has 7 when it likes to have 6. So taking away 7 from 6, we get -1 for its formal charge. So +1, 0, -1. In this version with the double bond between the nitrogen and the oxygen, we get 7 minus 7, so 0. Nitrogen's also 0. Oxygen's also 0. We don't actually have to do this to come up with the molecular geometry and the bond angles. I just wanted to do it for review, to cover it, so we're thinking about it. What number of electron groups do we have on our nitrogen? How many groups does our nitrogen have on it? Total number of clumps of electrons that are on or touching nitrogen. What's touching nitrogen? What are the electron things next to nitrogen? What's one of them? We've got a single bond. That's a group. What other groups do we have? We've also got a double bond. Do we have anything else on nitrogen? A lone pair. So we've got 3 groups. So we've got 3 electron groups on nitrogen. The number of electron groups determines the electron geometry. which would be trigonal planar. We weren't asked about that here, but it would be trigonal planar. How many bonding groups, how many bonds do we have? How many groups of bonding electrons do we have? 2. We've got a single bond. We also have a double bond. And we've got how many lone pairs? So thinking about our shape, 3 means that it's going to be trigonal planar for the electron geometry. And this can be helpful if we want to think through our shapes. If we want to just memorize it, or if we want to look it up on a table, it doesn't matter. We just look it up on the table. So our nitrogen in the middle, and it would look something like this for its shape. It's going to be this trigonal planar. Let's add a little balloon for our lone pair. If we imagine that this lone pair goes away, then what is left? What would that shape be called? If the lone pair is not there. Like if we keep the shape, the lone pair, though, it doesn't take up space. So what's this shape? Bent. So it's bent molecular geometry. So we're making the shape, and then we imagine that the lone pair disappears. We get bent molecular geometry. What are our bond angles going to be like here? If it was an ideal trigonal planar geometry, what would our bond angles be? We've got 3 of them on a circle. It would be 120 degrees. We can also refer to our table. This one, 11.1. So we're looking at 3 electron groups. We had 2 bonding pairs, or 2 bonding groups, 1 lone pair. So we get bent molecular geometry. The approximate bond angles, we would expect it if it was perfectly trigonal planar, it would be 120. But because we have a lone pair, this lone pair squishes the oxygen and the chlorine together. So this is going to be less than 120 degrees. Because the lone pair squishes them together. Try doing the molecular geometry of I3 minus. Our Lewis structure for I3 minus. We've got 3 iodines. Let's start off with putting them in a line. 3 with 7 electrons each. And we also have 1 more electron because of the negative charge. So we'll have 22 valence electrons. We need to get them connected. We'll put in 2 bonds. That's 4 bonding electrons. We should have 18 remaining electrons. We can give 6 to each of our terminal iodines, the ones that are on the ends. We just call them the end I's. That leaves us with 6 more electrons. Which we'll have to put somewhere. We put them on the middle one. How many electrons do we have, counting our octet for our central iodine? 10.
Oh, yeah.
Is that okay?
No.
Why not?
It's too much.
It would be too much. However, because we have iodine, iodine is in row 5. It has access to d orbitals. So it's got extra pockets. It can actually hold extra electrons into an expanded octet. So it's actually okay that iodine has more than an octet. There's no other way that we can avoid having an octet, because if we don't put them on the central iodine, they would have to go on the end iodine. That'll cause other issues. If we do formal charges, you'll see that that's the case. The iodine on the middle ends up having, for formal charges, a -1. The ones on the ends have zeros. The total of our formal charges equals the charge of our I3 minus. So that works out. Formal charges check out. If you do it with one of these lone pairs on one of the end iodines instead, it ends up being a 2- for the one on the end and a 1+ in the one in the middle. So for minimizing formal charges, this is the better shape. Now, thinking about our central atom, our iodine in the middle, how many electron groups do we have? How many clumps of electrons on that iodine? It's not 2. 5. 5 electron groups. It's got 2 bonds and 3 lone pairs. So remember, electron groups include bonds and lone pairs. If we had just the 5 electron groups, then it would be an electron geometry. It's still an electron geometry electron geometry is trigonal bipyramidal. That's our simple shape for 5 electron groups. And then we have to get rid of 3 of those groups. And our central atom, we had something that looks like this. This is our trigonal bipyramidal. If 3 of these are lone pairs, we want to put them in the equatorial positions, because then they're further spaced out from each other, versus if we put one on the axial position. And so this ends up being that our shape is linear. This should also be what you find if you go to the table 11.1. If you're confused, if you're feeling a little lost coming up with the molecular geometry, that's normal, that's okay, because there's a lot of different shapes. You will get better and more confident at it the more that you do it. I would recommend trying to do it in your head, or working it out on paper, or thinking about it, or posing it out, and then check the table and see if you're right, so that you start to build up some of that muscle memory, some of that crunching brain power type stuff. Questions about any of our geometries, electron groups, any of our shapes? Again, table 11.1 from the book is going to be a big help probably to you. Question?
Could you also put the structure in brackets and have a negative sign?
It should have a negative sign, yeah.
Okay. So it shouldn't look like that? That's what you should.
This is the electron or the Lewis structure that you should come up with, yes. When we are drawing molecular geometries on paper, So far, we've mostly been using these straight lines, and these are bonds that are flat in the plane of the paper or in the plane of the board. But we need to be able to draw things in 3 dimensions to be able to show some of these shapes the way that they actually exist. This becomes more important, especially when you get into organic chemistry. And so there's 2 different shapes that we can have, or 2 other things that we can do. We can do these hatched wedges or dashed lines or hashed lines. I will also typically just do this as an empty wedge because I never liked trying to get the spacing and the size correct for all of the little hashed lines. So an empty wedge also works for me. So these are bonds going into the page or away from you. And then we have these solid wedge lines that are coming towards you. Or out of the page. I usually just call this a hash line, and this I call the wedge. And the wedge reminds me of, there's a couple of things that it reminds me of. The first thing that it reminds me of is potato wedges, and I really like potato wedges. And so if I see potato wedges, I don't want them going away from me, I want them coming towards me because I want to eat them. It also sort of looks like pizza, and pizza is also yummy and tasty to me, so I also want the pizza to be coming towards me. So those solid wedges, those are going towards you because you want to eat them. The hashed lines are going away from you because that's the other option. If we're determining shapes for larger molecules, they're going to have more than one interior atom, so we would have to determine the geometry around each of the interior atoms, and we'll talk about that starting next class.